Today we're going to be talking about real numbers and their properties. And before we go too deep into the nitty-gritty of what's a real number, what are the properties, what properties are we allowed to use when solving equations, which is really why we care about these properties, let's also just do a quick little definition of square roots here. So a square root, whenever you see this symbol over a number of some sort, means what positive number times itself gives us this number. So in particular, if we had something like the square root of 64, that would mean what positive number times itself gives us 64, and we would say, oh, that's 8. Even though it's also true that negative 8 times negative 8 gets us 64, just for the sake of keeping a consistent definition, we roll with the positive number that gives us that result. However, if I try to ask something like the square root of negative 4, we would run into issues because negative 2 times negative 2 gets us positive 4, and so does positive 2 times positive 2. Therefore, there is no number in the reals that times itself gives us negative 4. So we just say that this does not exist, or often DNE for short. Sometimes this is also called undefined, not real, etc. Because as you go further in math, there is technically an imaginary number such that this would have a result. But for now, while we're sticking in the real world, no such number exists. So go ahead and pause your video real quick and try these next 3 examples on your own. So the square root of 0, that would be 0 because 0 times 0 gives us 0. The square root of 16 would be positive 4, since positive 4 times positive 4 is 16. And the square root of negative 9 does not exist because there's no real number in existence that times itself gives us negative 9. Now, of course, we might want to actually know a little bit more with what do we mean when we say real. So the real numbers encompass a variety of different types of numbers. The counting numbers is the innermost group. It is probably the first type of real number you ever encountered. It's numbers like 1, 2, 3, 4, blah, 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 all the way up to infinity where you're just counting by ones there. The whole numbers include all of the counting numbers, but also toss in the number 0. So 0 is not considered a counting number, but it is considered a whole number. Integers are all of the whole numbers, so we include 0, 1, 2, 3, 4, etc. But we also include negative 1, negative 2, negative 3, negative 4, etc. So all of the negative whole numbers. If it's a rational number, that includes all of the integers, but also any positive or negative number that can be written as a nice clean fraction. 1, 2, 3, 4, etc. are all technically fractions. They're just fractions over 1. But the rational numbers also toss on fractions like 15 over 7, or 1/3, or negative 3/4, etc. So anything that can be written as a fraction. All of these are considered real numbers. The other big family of real numbers that's not in this nested set are the irrational numbers. So that would be things like the square root of 3. If you tried to come up with what number times itself gives me 3, you would be running around in circles forever. There is no nice, clean, whole number times itself that gives you 3. No even rational number that times itself gives you 3. Square root of 3 is just its own thing, is considered an irrational number. It's still considered real. It doesn't run into the same issue as the square root of negative 9, where that just doesn't exist. It's still a real number. It's just not a very pretty one. It's just square root of 3, no other simplification possible. This also includes numbers like pi. So that is the never-ending decimal 3.14, blah, 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 blah. That represents the ratio between a circle's circumference and its diameter. It's considered a real number, but it's not rational. Things like e as well. This is also a number that you will encounter in further math classes. That has to do with continuous exponential models. It's a 2-point blah, 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 blah. Never-ending decimal. Can't be written as a fraction, but it's still a real number. So let's practice classifying some of these numbers. So go ahead and pause your video and try to answer these questions of which families each of these numbers belongs to. So if we take a number like negative 38, it's not considered natural or whole because he's negative. However, he is an integer. He is rational because all integers are rational. This is technically negative 38 over 1. And all rational numbers are real, so he is also considered real. Square root of 34 does not simplify. There is no nice clean number that gives us the square root of 34. The closest perfect squares are the square root of 25, because 5 times 5 gives us 25, and the square root of 36, since 6 times 6 gives us 36. But this does not have any nice answer like that. So that is considered irrational, but he's still real. If we have something like 4/5, that's not a natural whole or integer number, because it is not, 1, 2, 3, 4, etc., or negative 1, 2, 3, 4, etc. It is considered a rational number because he has a nice clean fraction that is the ratio between two integers, and he is therefore also real. If we have pi, that is not natural, whole, integer, or rational. He is an irrational number that is a never-ending decimal, which is also necessarily real as well. Now we're going to pivot into talking about some of the properties of real numbers. So this tells you what sorts of operations that you're allowed to do when dealing with numbers. The commutative property is whenever you are adding or multiplying, changing the order will give you the same result. So if I have any number, such as represented by A, plus any other real number represented by B, that's the same thing as B plus A. The same thing as A times B is B times A. Written here more concretely with numbers such as 3 and 4. And it works with, integers or fractions as well. If I have 1/3 plus negative pi, that's going to be the same thing as negative pi plus 1/3. Totally fine. And same thing with multiplication as well. Associative, so the way I would keep these straight is commutative. I think of moving. You commute, so they move places, changing the order, while associative has to do with who you associate with, so it has to do with grouping. So for addition and multiplication, we can change the grouping that goes on. So in particular, A plus B in parentheses plus C is the same thing as A plus B plus C in parentheses. So let's actually evaluate this to sort of prove to ourselves. So if I have 2 plus 3 plus another 4, I am suggesting that's the same thing as 2 plus in parentheses 3 plus 4. Well, 2 plus 3 gets us 5, plus 4 is going to give us 9. 3 plus 4 is going to give us 7, plus 2 is also going to give us 9. So that does indeed work. I would encourage you to go ahead and prove to yourself that this works with multiplication as well. Now for both commutative and associative properties, do you think that this also applies for division? I would say it does not. So for example, for the commutative property, it is not the case that 4 divided by 2 is the same thing as 2 divided by 4. Doesn't work. And then if you were to do the associative property, we would be saying if I do 4 divided by 2 divided by, let me actually make these a little bit bigger. If I were to do 100 divided by 2 divided by 2, if that were associative, then I could change the order of parentheses. So that would be something like this. 100 divided by 2 is 50, divided by another 2 would give you 25. Apologies for that alarm. Which would be one answer versus 100 divided by 2 divided by 2 is 1. That would be 100. So we just proved to ourselves division is not associative. So this only works for addition and multiplication. The distributive property is very specifically that we can distribute multiplication over addition that's found inside parentheses. So you'll often see it written in a textbook, something like this, that if I have A parentheses B plus C, that's the same thing as A times B plus A times C. This is most helpful when dealing with actual equations, which we'll get to a little bit later, but it's helpful to practice it first with just real numbers. So for example, 2 times 3 plus 4 in the parentheses is the same thing as 2 times 3 plus 2 times 4. You can also prove that to yourself. So if you were to simplify this a little bit on each side, you would get indeed that 14 is equal to 14, so we're good. You also can encounter this even if it was written the other way around like this. So you're still able to distribute that 2 to both of those numbers. Now, what allows us to do that? Well, that's actually the commutative property of multiplication right there. We just switch the order of multiplication and the property still applies. Identities are very helpful whenever you're thinking about what it really means to have things cancel out, or what it really means to solve equations. So the additive identity is what you can add to any number such that the number doesn't change. So it's 0 because anything plus 0 is just itself. The multiplicative identity is saying that when I multiply by this number, the original number doesn't change. That would be 1 because any number times 1 is itself. So for example, if I have 10 plus 0, that's just going to be 10. That's the additive identity in action. And if I have 10 times 1, that's just going to be 10. Again, that's the multiplicative identity in action. Additive and multiplicative inverses are often what allows us to solve equations. So if I have, and really the goal of an additive or multiplicative inverse is to get back to the identity. So for an additive inverse, I'm trying to find the number that I add to it such that when I added it, it ends up equaling 0. So for example, what do you think is the additive inverse of negative 10? That would be positive 10 because negative 10 plus 10 makes 0. So a lot of times whenever you're solving equations in the future, what you're really trying to do is find the inverse in this way. And similarly, the additive inverse of positive 5 would be negative 5 because 5 plus negative 5 also makes 0. The multiplicative inverse is what you multiply by to get 1, which is oftentimes the reciprocal. So for example, 4 times 1/4 would give you 4 over 4, which ends up equaling 1. Oftentimes the way we actually think about multiplicative inverse is division. So we would say, oh, well, 4 divided by 4 is going to give me 1, and that is true. And if I were to change this division using keep, change, flip, that the dividing by a fraction is the same thing as multiplying by the reciprocal, that becomes 4 times 1/4 is 1. These are actually the same statements. And this gets very helpful, especially when you're dealing with fractions, because let's say you were trying to undo or use the multiplicative inverse to get back to 1, let's say negative 3/4. Well, what would you multiply negative 3/4 by to get 1? That would be negative 4/3. If you don't believe me, multiply across the top. Negative 3 times negative 4 is positive 12 because a negative times a negative is a positive. And then 4 times 3 also gets you 12. 12 divided by 12 is 1, and we're back to the original. It's oftentimes stated that the multiplicative inverse for a would be 1 over a, whatever that number a might be. And then the additive inverse for a would be negative a, whatever that a might be. And by negative, I really mean opposite sign, because as we said, the additive inverse for negative 10 was positive 10. For properties involving 0, keep in mind that any number multiplied by 0 is 0. So if I have 100 times 0, that's still going to give me 0. 0 divided by any number except for itself is going to give us 0, because if I take nothing and divide it by 100 people, that's still nothing. But any number divided by 0 does not exist. That's considered undefined. Dividing by 0 is illegal math. Cannot do that. So just something to always keep in mind. So I would encourage you to pause your video and try these practice problems before I go through them. So for these practice problems, for the first one, identify the properties shown. Well, what we notice changed in between these two statements is simply the placement of the parentheses. So we're changing who we're associating with first. So this would be the associative property of addition. For the next one, actually very similarly, the only thing that actually changed was the placement of the parentheses. So this would be considered the associative property of multiplication. How would these, let's say I had 6 plus negative 6 plus 4. How would I use the commutative property for that instead? Well, commutative property would be changing the order, so I might change that to something like 6 plus 4 plus negative 6 instead. That would be the commutative property. Because commutative property changes the order, it physically moves the numbers around. What would be considered the additive inverse of 40? I actually said the answer. Of negative 40 would be 40, because negative 40 plus 40 makes 0. The additive inverse of 0 is already 0, is simply just 0. The multiplicative inverse of 2, however, is asking 2 times what would give me 1. So you really want to say 2 divided by 2, which means we're going to be multiplying by 1/2. While the additive inverse of 2 is saying 2 plus what gives me 0, and that would be negative 2. And this is more important than just having your definition straight. Whenever it comes to solving equations, you always want to be thinking about, do I want to be using an additive inverse to make 0 right now, or do I want to be using a multiplicative inverse to make 1 right now? We can also rewrite expressions using the distributive property. I would encourage you to pause your video and go ahead and try to rewrite these yourself. So to rewrite these with the distributive property, we're going to distribute multiplying by 4 to both of these numbers to get 4 times 3 plus 4 times 6. And I just will have rewritten that expression using the distributive property. Similarly, for the next one, we're going to do the same thing. That becomes 12 times 8 plus 12 times 2. There's several different symbols for multiplication out there. I'm choosing to use parentheses here just because it's helping me keep my numbers straight. If you had written something with a dot like this, that would also be completely acceptable. Or with the X multiplication symbol would also be acceptable. The only thing I'm going to say, though, is that you probably want to get out of the habit of using the X for multiplication, just because whenever you get deeper into algebra, X is oftentimes the variable we choose, so it can be confusing if you have 2 different types of X's floating around. This last one's actually asking you to work the other way around, where they have a 100 in common that was distributed over 5 plus 14. And then you could recognize that because they have 100 in common, we're just going to rewrite that once. And then the numbers that were not in common, we're going to rewrite as distributed over that addition. For these last sets of practice problems, I'm again going to encourage that you pause your video and try these yourself before I go through them. So here, anything times 0 is simply 0. However, dividing by 0 is undefined. If I'm saying 1 times negative 1 over 4 is the same thing as negative 1 over 4, and that is actually negative 1 over 4. It's just a little bit hard to read with the typing. That's saying that anything times 1 is itself, and that would be the multiplicative identity. So identity meaning that it is just like the thing that's always true. However, if I'm saying negative 3/5 times negative 5/3 is 1, that's the multiplicative inverse, because I just undid the negative 3/5 to get back to the identity of 1. Similarly, 4/3 times 3/4 equaling 1, that's going to be your multiplicative inverse, because I just undid that by multiplying by the reciprocal to get back to 1. While saying 5/2 times 1 is 5/2, that is just your multiplicative identity, because I'm just stating that multiplying anything times 1 gets back to itself. And finding multiplicative inverses is just a really good skill, so I would encourage you to go ahead and pause your video and try to find these multiplicative inverses yourself. So for 5/6, if I multiply by 6/5, that's going to be multiply across the top 30, multiply by across the bottom 30, 30 divided by 30 is 1. That's going to be your multiplicative inverse. For 0.9, I would actually encourage you to first convert 0.9 into a fraction, which is 9/10. And then you can see that its multiplicative inverse would be 10 over 9. Alternatively, you could have put 1 over 0.9, and that would have technically been correct. It's just not usually considered good form to put decimals in, inside of fractions. Not for any particular reason, just math conventions. For -2, the multiplicative inverse would be -1/2, because -2 times -1/2 gives us 1. And for -6/9, that would be -9 over 6, because -6/9 times -9 over 6 gets us 1. And if you just want the different properties in sort of short form, these would be considered the different properties. The only thing that is missing on here is that for associative, you also have the associative property of multiplication as well, which symbolically would be considered that.